Does it say got it?
Yeah, we
Oh.
actually my lunch. Yeah, it's going well. We hit the ground running.
Don't be nice, I could invite them. Basically, out of the picture now.
It's a lot of it's gonna be much different.
Next circle.
So it's fun. It's really fun.
Finance companies. All of the actual like so much easier to use finance companies. Yes.
Unless there's something else. No problem.
So. They don't. I mean, I don't want
They're existing.
Yeah. That's
Sure. Should I stand here or on the other side?
Up to you. I think people do both. It's like a 50-50, whichever is more.
But you see my, yeah, you see my, okay, okay.
Yeah.
Maybe not.
Yeah. Yeah, exactly. Maybe that's not a good idea. You're ready?
Okay, so let's get started. So today we're extremely happy to restart the Physics Club series with Professor Alberto Nicolis from Columbia University. Alberto is well known for many contributions to both high-energy physics and cosmology. And so these include, for example, the conjecture that gravity is the weakest force, modifications to Einstein's theory of relativity, and studies of their cosmological implications. And more recently, studies of the impact of breaking of space-time symmetry on condensed matter systems. And so today he's going to tell us about some work in this direction and a generalized Archimedean principle. So go for it.
Thank you very much. It's really a pleasure to be here, and I'm having a wonderful day talking to some of you. So I want to talk about something that sounds quite mundane, and it's certainly more than 2,000 years old. And you might be wondering, okay, what more do we have to learn about Archimedes' principle? So I want to try to convince you that there's a novel way to think about it, and we can make new predictions if you think about the Archimedean principle in this way, and we can actually try and test them. And in particular, I don't know what happened. I will use these ideas to derive a general formula for the mass transported by a sound wave. So usually we think of a sound wave as a, let's say, if we think about the sound wave packet, so it's sort of localized and it moves in space in some medium, let's say air or water, and there is a rarefaction and there is a compression, a rarefaction and compression. And we think, using some linear theory intuition, we think of these oscillations as averaging out, and so nothing in the end is left after a sound wave has passed. There's no perturbations left. So I want to convince you that in fact a sound wave carries with it mass, carries with it part of the mass, a tiny fraction of the mass of the medium it propagates in. And in general, for generic fluids, typical fluids, that mass is actually negative, so it leaves some mass behind. Okay, so how do we get there? So the question one can start with, sorry, let me scroll. I don't know how to scroll. How do I go to the next slide? So this is going to be the only slide I'm able to show today. Okay. So maybe I exit.
It may just be that it's in Zoom. So you just exit and then make sure you're in the.
I see page 1. Okay, somehow it wants me to go back. Okay, now I can go forward, but no, okay, I don't know what's going on. Okay. Yes, it works. So the question I want to ask, and then we'll take a long detour to answer this question, is if you take a fluid, let's say like water, and you look at a sound wave packet in water, and there is gravity, okay, and you shoot this wave packet parallel to the surface of water, so orthogonally to the gravitational field. And the question I want to ask is, does this sound wave want to float or want to sink, or neither? Somehow these concepts do not apply to sound waves. So, okay, it might be an arbitrary and confusing question, but it's still a physical question, no? So we can actually test, in principle, experimentally, we shoot a sound wave orthogonally to gravity. Is there any net buoyancy on this sound wave? Is it positive or negative? So, and also, in terms of the Archimedean principle, usually we are thinking in terms of, okay, what's the total mass of the sound wave, and there will be a gravitational pull on it, and what's the total buoyancy, the back reaction somehow of the fluid onto the sound wave, and there will be an uplift associated with that. And so let's go back then to Archimedes' principle and try to see what we can learn from there and what we cannot learn from there. So if I take a solid object and I immerse it in a fluid, there's only two quantities I need to know to determine whether it's going to sink or float. Okay, one is the mass and the other is the volume. So the mass tells me how gravity will act on this solid object, and it will be a force directed downwards. And the volume, assuming the object is a solid object, so it doesn't change its volume when I immerse it in water, the volume will tell me how much fluid it displaces when you put it there, okay? And this is the phrase that we use, the fluid displaced. And the volume of the object times the density of the fluid will tell me how much mass it has displaced. And one can prove in general by applying some Gauss theorem that the vector sum of all the pressure forces acting on the object, since pressure is higher at higher depths and lower at shallower depths, the vector sum of all these pressure forces will be non-zero. It will be directed upwards, and it's exactly the mass of the object times the gravitational acceleration. So it's the weight, sorry, it's the mass of the fluid displaced by the object times the gravitational acceleration. So it's the weight of the fluid displaced. Now I'm going super slowly, even though this is trivial, you all know this, because you see how subtle now it can be to try and generalize it to other things. And then when you compute the total force, which is this tiny arrow here, in this case, I took a solid that is heavier than water. So there's a tiny force that wants the object to sink. Okay. Now, how can we generalize this to more generic objects? And now I'm going to use object in quotes. For instance, I will call a wave packet of sound, for instance, an object. Why? Because like in the geometric optics approximation for light, we can actually think of wave mechanics at short wavelengths and for localized wave packets as essentially particle mechanics. Okay, so there is a reasonably well-defined position of a wave packet, and there is a reasonably well-defined momentum, and there is a reasonably well-defined trajectory. And so we can think about, okay, what is the trajectory of these generalized objects? Okay. So this is one of the objects I can think about when I want to generalize the Archimedean principle. Other objects could be just microscopic particles. Suppose you drop an electron in water. Does an electron want to float or sink? There you see, I mean, quantum mechanics is so important there that it's not even obvious what the volume of the electron is, no? And certainly it's not obvious what the volume of a wave packet is. In fact, these two concepts are related because also the electron can be thought of as a wave, no? There's a wave function associated with an electron. And so what is the volume occupied by that wave function, okay? So in particular, if I go back to the Archimedean principle, I need to know the volume of my object and the mass. And in the case of waves, or in the case of quantum particles, I don't know, certainly I don't know the volume. For quantum particles, maybe I know the mass. For instance, the mass of the electron I know pretty well, but certainly for a sound wave, I don't even know what the mass of a sound wave is. And notice that in particular for excitations that only live inside the medium I'm talking about, let's say sound waves in water, there's no way I can take that object out of the medium and measure some of its properties there. No? Here in the Archimedean principle, to measure this mass, I need to take the object out of the water. Okay? There's no way to measure the mass in water. In particular, you could say, oh, come on, but mass is also inertia, so I can try and push the object with a given force and measure the acceleration. But that's not what happens in a fluid, meaning that's not the only ingredient that contributes to the acceleration of fluid, because already in the ideal fluid limit, when you can neglect viscosity forces, when you move in water, in fact, you've tried probably in a swimming pool to walk through water, it's so much more difficult because you're dragging with you a lot of fluid. You're dragging with you an amount of fluid of the same order, but not quite the same. It really depends on your shape. Of the same order of the volume displaced. So even inertially, you cannot measure the mass of the object in water. So there are some things that you can measure only if you're able to take the object out of water. And certainly I cannot take a sound wave out of water. Or for instance, in air, I can have sound waves, but they're different sound waves. So the two parameters that I need to know to compute the net buoyancy force on a generalized object like a sound wave, I have access to neither of them. And in fact, in a case like this, they're not even well defined. I don't even know what I mean by that. Okay, so the question that we started with, which is simple to phrase in terms of just following a trajectory, for now is unanswerable. Okay, so in order to answer it, let me go back again to ordinary objects. And let me show you that for certain objects, there's already a subtlety there, but this subtlety will also tell us how to get out of the impasse. Okay, so let me consider a sponge, okay, the ordinary kitchen sponge, okay? I can have two alternative descriptions of the sponge once I drop it in water. I can have a microscopic description in which I'm really able to look at the fine structure of the sponge, so which here, given my very limited artistic skills, I'm just denoting with a regular mesh, okay? But by this mesh, I simply mean that the sponge has very many microscopic cavities, okay? And if I applied this very sophisticated microscopic description, the Archimedean principle takes this form. I have a very little mass of my object, which is the mass of the dry sponge. And I also have a very little volume that the sponge, the solid part of the sponge takes up, okay? So it's just the volume of the lines in this mesh in my rendering of the sponge, okay? But you can think of it as just the volume of the solid part of this sponge. But given how many cavities the sponge has, these two quantities are small, okay? Most of the dry sponge is most of my sponge is empty space. And so I have a small, again, in my symbolic rendering, these are small arrows and these are long arrows. I have a small buoyancy force because the volume displaced is small. And I have a small gravitational force because the dry sponge mass is small, okay? Now, suppose you are a diver, okay, and you've never seen a dry sponge in your life, and maybe your vision is also blurry because you dropped your mask, okay? What you see is a slab. You see a sponge underwater. It's a slab, and you cannot make out the fine mesh, okay? And so for you, the volume occupied by this slab is pretty large, is the whole slab volume here filled out. And the mass of this now wet, soaked sponge, if you were to take it out of water and weight, it's pretty big, okay, because it absorbed a lot of mass. And so it has a large mass now and a large volume. And if you compute the buoyancy associated with this volume and the gravitational force associated with this soaked mass, they're pretty big. But the net vector sum of the two is the same as before. Okay, and simply, what's the difference between the two descriptions? The difference is that the water that got soaked up by the sponge in this description contributes in exactly the same way to the buoyancy force and to the gravitational force. You are just adding to both vectors the weight of the water absorbed by the sponge, okay? Now, this tells you a few things. This tells us that depending on the description that you take, for a system like this at least, the role of the physical quantities that we were talking about can change, okay? And their magnitude can change. And the splitting of the buoyancy, of the net buoyancy force between a buoyant term and a gravitational term is not particularly invariant, I would say. It's not particularly intrinsic to the system. It's more an artifact of your description of the system. And on the other hand, the net force that is exerted on the sponge, which, by the way, is the only thing you can measure in water. So if you're never able to take out the sponge from water, that's the only thing you can measure, the net force acting on the sponge. That's the same in both descriptions, okay? So those of you who are familiar with particle physics and quantum field theory can recognize here something similar to what happens in renormalization theory. Sometimes in particle physics, we have to come up with a mathematical way to deal with infinities. And depending on how we do that, things are defined in slightly different ways. And depending on our resolution, which in this case would be the difference between being able to resolve the mesh or not being able to resolve the mesh, things can get moved around, okay? But we always insist that the physical quantities that we can measure are completely independent on these details of how we implement the renormalization program, okay? So here I see something similar, okay? And so let me emphasize again, the thing that is invariant is in fact, between the two descriptions, is in fact the thing that is directly measurable in water. So maybe it's something good to focus on, since it's both measurable and it does not depend on the description that we have for our system. And on the other hand, how we split that measurable quantity in the two contributions does depend on our resolution and how we decide to talk about the water absorbed by the sponge. Is it part of the water or is it part of the sponge? And this is great for us because if we go back to our sound waves, we have no way to determine either one of these two contributions. So maybe because we don't know what the mass of a sound wave is and what's the volume of a sound wave is. So maybe we shouldn't even try to determine those two contributions, and we should just focus on determining the net force applied to a sound wave, okay? Notice that I've been talking about objects immersed in fluids and the Archimedes principle. So what I'm gonna do next is to try and apply these ideas that I just mentioned, how to just focus on the net effect. And as a bonus, we'll be able to generalize the Archimedes principle not only to more general objects like sound waves, but also to dynamical, very dynamical situations. Now, because Archimedes principle, it's a statement about hydrostatics, okay? But once we start talking about sound waves, well, a sound wave cannot stay put, okay? It has to move at the speed of sound, so it's a very dynamical situation. Not only that, but the sound wave does not obey F equal ma, okay? For instance, since the sound wave is moving at the speed of sound, there is no way to push it from the back and make it accelerate even by a millimeter per second, okay? The velocity of a sound wave is fixed, so there's no way to accelerate it. So it means that our language in terms of forces has to be generalized as well, okay? And, or if you want, talking about forces is a very good idea for non-relativistic systems, which is the one we're talking about now, but in empty space. The moment you live in a medium like water, and the moment some things can only exist in a medium like sound waves, the language of forces can be very deceiving and very inappropriate, okay? And so the main idea, which builds on many previous ideas that have been developed maybe in the last 20 years for these particular applications. And in particular, some of these ideas I took from Walter's old paper about gravitational wave effective theories from binary systems.
Not that old.
Well, it kind of is. I think it's 19 years this year or 20 years. We are kind of old, so yeah. Anyway, so it's a fantastic paper about how to use effective theories to talk about localized objects and sources. And in particular, you can think of what is an effective theory. Well, in particle physics, we talk a lot about effective field theories. Here, I'm going to talk more about an effective point particle theory. But you can think of effective theories as a generalization of the multiple expansion of electrostatics. So you've all seen that for sure. So if you take a complicated system of charges or even a continuous charge distribution, and you try to probe it from large distances, typically much bigger than the size of your object, of your distribution, then you know that you can essentially perform a Taylor expansion in the size of your object over the distance at which you are probing your object. And you can replace all the microscopic complexity of your object with a number of physical quantities associated with the charge distributions that are the so-called multiples. And you start with the monopole, and you have a dipole correction to it, and then you have a quadrupole correction to it, and so on and so forth. And each new multiple that you add is down by 1 power of the size of your object over the length scale at which you are probing physics. In terms of its importance to physical observables. For instance, if you were to compute the Coulomb potential far away here, okay, you start with a 1 over r times the monopole, and then you have a 1 over r squared times the dipole, 1 over r cubed times the quadrupole, and so on and so forth. Okay, so it's a systematic expansion in the size of the object over some other length scale. Okay, and so what I want to do here is to use effective theories where the degrees of freedom of the object I'm talking about in, let's say, water is just the positional degrees of freedom where it is. And you can think of coupling this object to the surrounding fluid in all ways allowed by the symmetries. Okay, I'm going to do that with the Lagrangian first, and then I'm going to turn to the Hamiltonian for technical reasons. And as long as the surrounding fluid has typical variation scales much longer than the size of your object, you can use the same idea as here. You can start with the simplest possible terms that only take into account the position of your object, and then you can add the dipole-like terms that take into account, for instance, the orientation of your object, if your object is not isotropic, etc. Okay, so on and so forth. And why is the fluid not completely homogeneous? Well, certainly there is gravity. That's our starting point. We want to talk about system with gravity. So there's going to be some modulation of pressure under gravity. And also you can generalize the same ideas to cases, dynamical cases in which you have, I don't know, some flow of your fluid or some pre-existing sound waves, let's say long wavelength sound waves interacting with your object. Okay, so this is a very general approach that takes into account how your object can couple to the surrounding medium. And there's in this approach there's two simplifying aspects. One is this multiple expansion that we already talked about. Somehow it's automatically an expansion in the size of your object, and with each new multiple, you're essentially adding an index, so you're adding more and more structure if you want, but the lowest order ones have very little structure, so there's not much you can do with them. You cannot contract them. You cannot contract indices with anything else if you don't have indices, for instance. Okay. And the other is, which is a fundamental now mantra in physics for many decades, is the power of symmetries. Okay, if we isolate the symmetries of the system, and if we have enough symmetries, then the dynamics that we can write down are very constrained. Okay, and so for us, the symmetries are going to be translational symmetries, rotational symmetries, and Galilean boosts. Crucially, that happens to be important. So perhaps one of the unexpected outcomes of this approach is that there is, in fact, a connection between the Archimedean principle and Galilean invariance, even though inside the fluid, Galilean invariance is broken. So even though the fluid picks a frame, the fact that fundamentally the dynamics have to be Galilean invariant places some constraints. And now the idea will be also to start without gravity, and we will see later how gravity can be added essentially for free to this approach. Okay, so this is the basic qualitative picture. And now let's see some details. So I claim, and again, there's a number of ways to come to this result. You can even start from a relativistic effective point particle theory interacting with the medium and then take the non-relativistic limit. Or you can start directly from these considerations here in terms of symmetries. But the idea is that to lowest order in these multiple expansions, so the monopole interactions that a particle can have, are of this form. So the Lagrangian of my point particle that can depend only on its position and its velocity, to lowest order in these expansions that I'm talking about, is a function, a generic function in principle, of the relative velocity between my point particle and the fluid. So U is the velocity field of my fluid. And this is where Galilean invariance enters, okay? The fact that there's a relative velocity here. And absolute value, because we're writing down a system that is invariant under rotations, and with potentially with some dependence on the fluid density. Okay, so for now, I haven't constrained much the system because I'm still giving you a generic function here, f, but at least I know that this generic function can depend on the position and velocity on the object through these combinations, the relative velocity between my particle and the fluid, and the density field of the fluid. So the dependence on position is secretly in here, rho of x, and in here, u of x. In fact, even in dynamical situations, you can prove that as long as the time variation of the fluid motions that you can have, like a flow or a sound wave, therefore, as long as that frequency is much smaller than the sound crossing time associated with your object, meaning the time that it takes a sound wave to cross your object. Okay, so if the frequency of these variations is much smaller than that inverse time, if you want, then this Lagrangian that you write down here still describes the most general way you can couple a small object to your fluid. Okay, so in particular, this describes also interactions with sound waves. Okay, this is interesting because now I'm going to relate this F to buoyancy, to the Archimedes principle. So it means that by doing static buoyancy experiments, you can actually measure the parameters that determine the couplings of your object to sound waves. So you see how useful this viewpoint is, that you can do static experiments on an object, and then it tells you that when you shake this object, it tells you how much sound wave, for instance, it emits, or how much is shaken around when a sound wave comes. Okay, and again, the organizing principle here is the same as in the multiple expansion. And so in particular, we can only talk about wavelengths much longer, lambda wavelengths much longer than the size of the object. Okay,
Are you assuming that the fluid is a fluid?
Good. So very good. So this viscosity, which is the first correction to perfect fluidity, is also down by inverse powers of wavelengths. So what I mean is that at long enough wavelengths, viscosity is always negligible. All fluids become perfect at long enough wavelengths.
What boundary conditions?
I'm-
Something floating, right?
Excuse me?
Boundary conditions.
Yeah, here I'm considering bulk dynamics, so essentially infinite fluid.
What boundary conditions at your small body?
Yeah, the crucial thing is that it doesn't matter, meaning different boundary conditions will inform what the function f is. But the point, you see, the power of this approach is that boundary conditions are replaced with interactions.
If you assume that the fields are continuous, perhaps yes, but if use is continuous, then perhaps no.
Well, and the claim is that yes, that's one of the general properties of effective theories, that boundary conditions at the boundary of your source or object in the point-like limit get replaced by interactions.
Yeah, if it exists, yes.
Hmm?
If the point-like limit exists, yes. If it doesn't exist, then no.
Well, but I'm taking a pragmatic viewpoint in which anything localized from very far away looks like a point, no? Would you agree that in electrostatics the multiple expansion is a general parametrization of any localized charge distribution from very far away?
For one bridge interaction Coulomb is true here. But you can
Yeah, it's a longer discussion, but yeah, I'm only talking about long distance perturbations in the fluid. So in a sense, I'm only talking about the long distance fields in your language. Okay. So now, okay, so let's now give a more modern characterization of Archimedes' principle using these ideas. Okay. So from this viewpoint, you see, what does it even mean to talk about an ordinary object? Like you were saying, we're not even specifying whether it's a solid object with fixed boundary condition. What about our sponge? Our sponge, what are the boundary conditions for our sponge? Again, it depends on the description that we have in terms of microphysics versus macrophysics. So an ordinary object, it so happens when you, and again, I'm not giving you any proof, okay? I'm just telling you what you find by applying this logic systematically. An ordinary object has a low enough velocities, low enough compared to the speed of sound, as a Lagrangian that looks like this. So it has a kinetic energy associated with each mass in vacuum or air, okay, in empty space. Then there is this extra mass that you get, I told you about, when you try to walk in water. It's much more difficult because you are dragging with you a lot of fluid, okay? So this gets captured by this coefficient. And by the way, this I'm not the first pointing out this. If you open Landau and Lifshitz fluid dynamics, you will find these corrections to the Lagrangian for an object. In fact, you can even show here. I'm not going into that those complications because they are irrelevant for us. But you can even show that for an object that is not isotropic, so for an object that is not a sphere, this coefficient is in general a tensor. Okay, so you can have a tensor mass in a fluid, which is something you cannot have in vacuum. Okay, and then if you think about it, okay, so these are the kinetic energies that an ordinary object are. If you think about it, to actually put an object in a fluid and bring it to a region, regardless of what the density is, if in the end they have to end up to a region of pressure P, okay, I must pay an energy price. It's a potential energy, essentially. Pressure times the volume of the object, simply coming from the first law of thermodynamics. The energy needed to make room for volume V at pressure P is PV, okay? Assuming, of course, the pressure is approximately constant over V. Then if it's not, then this is another higher multiple, okay? So this is the work done against the pressure P. This is the kinetic energy associated with the fluid dragged by an object, and this is the kinetic energy of the object itself. Now, it's not immediate, but you can manipulate a little bit this equation, this Lagrangian, and use the Euler equations for the fluid. So it applies also, what I'm going to say applies also for the for a dynamical situation. And you end up with a Lagrangian of exactly the form I told you about. So it's a function just of the relative velocity, and the coefficient in front is m plus delta m. And then, apart from the PV part that you have here, you have another source of potential energy. So after these manipulations, if you want to rewrite, if you want the Lagrangian in the form that I was asking you to use, there is another form of potential energy, which is the mass of the object. So it comes from manipulating this part of the Lagrangian, times this function W, which is the integral in rho of dP over rho, differential of the pressure over rho, okay? This is a classic, for instance, this is the same as Bernoulli principle, but written in different form. So you have these thermodynamic quantities, okay? Crucially here, everything only depends on rho or on P. You can choose the thermodynamic variable you want. Okay, so now we have our Lagrangian written in the form that I had asked you to use. And so apart from the kinetic energies, now we have these two forms of potential energy. One is the one directly coming from making room for my object. The other is a potential energy coming from the kinetic energy of the object when I manipulate it to rewrite it in this form. It's not obvious why it's there. It comes from, again, a differential form of the Bernoulli principle. So now, what about gravity? Well, now let's introduce gravity. So the gravitational acceleration is the gradient of a potential, the Newtonian potential. Remember, the Newtonian potential is the energy per unit mass in a gravitational field. And now I look at some hydrostatic configuration. So you see also, it's kind of confusing the process here. We start with a dynamical, fully dynamical Lagrangian. It's important how we write the kinetic energy, etc. But in the end, we are only interested in hydrostatic. So there is an interesting interplay going through Galilean principle of relativity between kinetic energies and what happens in hydrostatics. Kind of confusing, but I mean the algebra is pretty simple. So if those of you are interested, I can show you what's going on. So the hydrostatic equilibrium configuration relates the Newtonian potential to the pressure, and so in particular, and also to that other function W, because this function W is related to the pressure. And so it tells us, it relates the gradients in particular, but these equations can be integrated. And so up to integration constants, both the pressure at any position and this function W, this other potential W at any position, are uniquely determined by phi, but in an algebraic way. You don't have to solve a differential equation, okay? It's, you see here, for instance, in this particular equation here, I can just drop the gradient. So I get that W is minus phi plus a constant. It's an integration constant that I don't care about. And here it's the same because P is only a function of rho. So gradient of P over rho is still the gradient of a function of rho. So again, I can drop the gradient again. So bottom line is that what you get is that if you start from this Lagrangian, and now you compute the derivative with respect to x of the potential energies to compute the force, this P and this W are completely determined by phi. And so you get a force that just depends on the gradient of phi. But the gradient of phi, by definition, is the gravitational acceleration. So you get the net force acting on your object. And it happens to be, if you look at all the steps that we've done, precisely the gravitational acceleration times the mass of the object minus the mass of the volume displaced. Okay, so this is a cumbersome way to rederive what Archimedes derived by intuition more than 2,000 years ago. Okay, so it's not clear what we are gaining, but we are gaining generality. Okay, because Lagrangian mechanics and the Hamiltonian mechanics are extremely general frameworks, and now we can apply the same logic to whatever can be described by Lagrangian or Hamiltonian. Okay, but this is how you rederive the Archimedes principle from effective point particle theory for a particle immersed in a fluid. So now, let me generalize it. Okay, the claim is this, and for technical reasons, it's better to do it at the level of the Hamiltonian rather than the Lagrangian. So I'm just going to tell you what the rules are, and for those of you who are interested, I can show you the algebra later. So the rules of the game are, okay, take your object and first of all, switch off gravity, forget about gravity, and try to write the Hamiltonian, which is always, remember, a function of x and momentum p, as a function of the momentum p, and the dependence on x can only come from the modulations of the density or the pressure. Again, it's a symmetry principle. Whenever the pressure is constant and the density is constant, the energy of your object cannot depend on x. Okay. So now, the equation of motion. Notice here I still considered the force because I know that for ordinary object a force is a good way to classify, to characterize how other systems, in particular the fluid, are acting on my object. But in general, I don't have equations like F equal ma for more general objects like sound waves, but I still have Hamilton's equations. That's why somehow this viewpoint is also useful. I know what the equations of motion are for a generic Lagrangian or Hamiltonian. There's a systematic way of deriving equations of motion, whereas there is no systematic way to generalize F equal ma if we don't use Lagrangian or Hamiltonian mechanics. And so in particular, one of the Hamilton's equations of motions tells us that the derivative of momentum with respect to time is minus the gradient of the energy with respect to x. And now we apply the same logic as before. We relate the local values of pressure, W, density, all these quantities to just the local value of the chemical potential, sorry, of the Newtonian potential. And so after some straightforward manipulations that relate P to phi, and also the derivatives of the pressure with respect to the density, to the speed of sound, you derive this general formula here, okay, which is quite compact. The way the momentum responds to a gradient of the Newtonian potential goes through this function. You're supposed to derive this function, energy, the energy function, with respect to the density in terms of logarithmic derivatives. And then you have E over speed of sound square. Okay? Now, by definition, if you want, this coefficient up to a minus is the gravitational mass of your object. It tells you how your object responds to a gradient of a Newtonian potential. So this defines the gravitational mass, okay? And in particular, in this particular case, it was precisely the net gravitational mass of our famous sponge, okay? It's the difference between the mass of the object and the volume and the mass of the fluid displaced. So it's the net mass that, if you multiply by the gravitational acceleration, gives you the net force acting on your object. So that's it. That's the recipe. The net gravitational mass of an object immersed in a fluid is this logarithmic derivative times energy over speed of sound square, when you parameterize the energy as a function of momentum and density. Now, the interestingly enough, mass is proportional to energy over speed of sound square. Now, I don't know, you can speculate what the relationship is with E over C square from relativity. I think at this level is just dimensional analysis, meaning energy as units of mass times some velocity square. In the fluid, the only interesting velocity is the speed of sound, so that's what you get. But you see the speed of sound here comes from here. When you derive with respect to x, you have a derivative with respect to the density. The derivative with respect to the density and to the pressure are related by the speed of sound, and the pressure is directly related to the Newtonian potential. So that's how the speed of sound comes in. Okay, so let's go back to sound waves. Now we have a sound wave packet. What is the energy of a sound wave as a function of momentum and density? Well, we can use some quantum mechanical intuition. If I have, certainly I know that the speed of sound for a classical sound waves relates frequency and wave number. So if we multiply both sides by h bar, this would be, the left-hand side becomes the energy of a single quantum, and the right-hand side, k times h bar, becomes the momentum of that quantum. So a good guess is that the energy of a sound wave is the speed of sound, which crucially depends on the density or pressure, times the momentum. And if you want to convince that this is exactly the correct Hamiltonian for a localized sound wave packet, you just use the other Hamilton equation, the one we didn't talk about, that tells us that the velocity of an object with a given Hamiltonian is the derivative of the energy with respect to the momentum, which in this case we get exactly the speed of sound times the unit vector associated with that momentum. So this is the Hamiltonian of a sound wave, in the case in which we are using the localized wave packet approximation. And so if we apply our formula, we are supposed to take the logarithmic derivative of energy with respect to density. The energy depends only on the speed of sound as far as density is concerned. So we get the logarithmic derivative of the speed of sound with respect to density times energy over speed of sound square. And this is typically negative because this logarithmic derivative is typically positive. For denser fluids, you usually get higher speeds of sound. Okay. Now, this is a way to derive this formula. After this, we have checked it in a number of ways. In particular, we've checked it by taking the continuity equation and the Euler equation, and at linear order. So you first look at the sound wave, okay? So a linear solution of the linearized equations of motion, and you do discover that. Sorry, I'm going to write down something here. You do discover that, as I was saying at the beginning, not surprisingly, at linear order, rarefactions and compressions average to 0, and you don't get any net mass. But then you can ask yourself, okay, now suppose I look at perturbations in the mass density, and I go all the way to quadratic order. So I solve the equations of motion or hydrodynamics at quadratic order in the perturbation, okay? And then I integrate these in a volume, large enough volume that surrounds almost completely the wave packet I'm talking about. So I define this as the mass, the gravitational mass, if you want, transported by the sound wave. And if you do this at second order, you get exactly the formula I'm talking about. Okay? Excuse me?
How do you measure it?
That's a very good question. Okay, but let me come to that. Okay, let me come to that. For instance, I had an idea about, for instance, in as far as I can tell, in cold atom experiments, one can monitor very precisely the density field. Okay, so I was thinking, okay, if one is able to set up a sound wave, and then one can take the integral, this integral, like numerically, one can check whether it obeys this equation. That's an idea.
Why do you call that as white, just not water?
Because it's not easy to monitor to monitor precisely density in water. You see, you have to monitor all these oscillations precisely. Okay, they mostly average to 0. So,
What is the scale of this legal set you draw?
well, I don't know, whatever the experiment can do, but there's going to be a typical wavelength.
Is it different from the sound wavelengths?
I'm talking about sound waves here.
Sound waves in water, you know, it's pretty big. It's substantial length. Depends on frequency. Whales communicate by sound.
Yeah, but also if you do this underwater, you can hear it. So it can have many different wavelengths depending on the source. But yeah, in principle, I think it's not easy to have a very precise map of the density field of a fluid because it's water in water. So even just in terms of imaging, it's not obvious how to image. But I understand in cold atom experiments, they can do that very precisely. But I have another idea about to measure it, so let me come to that in a second. What I wanted to say here is that, yeah, so even though we got to this final equation here in a sort of very cumbersome way, one can just start from continuity and Euler equation, solve them to second order for a wave-like solution, and then compute this integral. And this integral exactly amounts to that. Notice that crucially here, you see here I'm telling you you have to go to nonlinear order. So it matters what the self-interactions of the sound waves with themselves are, okay? And this is captured by this quantity here, okay? If a fluid had no self-interactions of sound waves with themselves, the speed of sound would be constant in density. So the two things go together. The fact that the speed of sound depends on density is related to the fact that sound waves interacts with each other. And second interesting property of this is that this is completely determined by the equation of state. So if you give me a fluid for which you know the equation of state, for instance, in the form pressure as a function of density, this derivative can be computed, okay? So I also want to measure, I also want to mention that there is something about this result that makes it look fake, okay, in the following sense. You know that if you take a fluid under gravity, okay, there's going to be a stratification, a continuous stratification, whereby the pressure depends on position. And again, in general, this also implies that in particular, the speed of sound depends on position, okay? And like for electromagnetic waves, when you have a material with a modulated index of refraction, you can have refraction phenomena. In particular, you can have Snell's law. Okay, Snell's law in this language is very easy to derive. We have conservation of energy because the Hamiltonian we wrote down is time independent. We have conservation of horizontal momentum because the Hamiltonian we wrote down is translational invariant in that direction, not in Z, but in that direction it is. So if I take the ratio of these two, I get that the cosine of this angle that my trajectory forms with the horizontal over the speed of sound must be constant along the trajectory. And this is Snell's law, okay? So the result we derived about this fancy gravitational mass, net buoyancy, etc., is nothing but refraction. So one could object that this has nothing to do with gravity, okay? But I claim that maybe Snell's law is degenerate with gravity, but this definitely has to do with gravity. And the reason is that since the effect comes from a Hamiltonian or an action that describes the interaction between our object and gravity, not only does our object respond to gravity, but gravity responds to our object. So interactions go both ways, okay? This is, if you want, the generalized action and reaction principle of Lagrangian or Hamiltonian mechanics, in the sense that once an interaction term is in the Lagrangian or the Hamiltonian, it affects both parties that participate in that interaction. So I claim that with our with the sound wave, there's a very physical mass that travels with it. In general, it's negative, so it's a mass that is sort of left behind. And that mass sources gravity. So in principle, another way to measure this, coming back to your question, is to follow whether there is a perturbation in the gravitational field that travels with the sound wave. Now, of course, in the lab, you cannot do it, but one potential idea that we've been discussing with LIGO people at Columbia is, okay, when there is a pretty energetic seismic wave going under LIGO, can one use LIGO to actually measure the perturbation in the gravitational field? And let me just conclude with this, that maybe since we were talking about liquid helium earlier, maybe this is interesting from some of you. So this generalized principle that I gave you here, this one, can be applied to anything. If you give me the energy as a function of momentum and density, I'll give you the gravitational mass and the associated net buoyancy. So there are these peculiar excitations in liquid helium called rotons. So if I plot the energy as a function of momentum, it starts linear, and these are phonons, which are quanta of sound waves, and then it develops a minimum, okay, with some gap. Now, the minimum at finite momentum is very interesting from the mechanical viewpoint, because you see, remember, the velocity is the derivative of the energy with respect to momentum. This is essentially group velocity. No? Now, if I am right of the momentum, this derivative and momentum itself have the same sign. So I have positive momentum and positive velocity. But if I am left of the minimum, this derivative has the opposite sign. So I can have momentum that way and velocity the other way. So I can have excitations that move that way, but carry momentum pointing that way, okay? Now remember, our Hamilton equation tells us dp over dt. It doesn't tell us dv over dt, it tells us dp over dt. So for rotons, one can apply our formula and figure out that the mass, the gravitational mass carried by a roton is positive. This is the net gravitational mass. So rotons want to sink in liquid helium. But since their velocities, depending on when they are, where they are here, can be anti-aligned with the momentum, they can have funny trajectory. If your trajectory is such that you go past the minimum once or twice, you can have inversion phenomena. And so rotons can have trajectories like this in a gravitational field. Here I'm plotting a gravitational field going down as usual. So they can have pretty mundane parabolic trajectories like this. But they can have funny trajectories like this one in which there is two inversion points. The claim is that this, if you were able to monitor the trajectory of a roton under gravity, only gravity, in liquid helium, you could observe phenomena like this. I don't know whether this is measurable, but this is certainly something I've never seen before. So my conclusion is this, that even though Archimedes' principle is very well known and certainly true, it can still be phrased in novel ways, and we can learn something about it by phrasing it in that way. In particular, we can phrase it as an interaction, as a net interaction with gravity. And in that language, it can be generalized to all sorts of objects, including quantum particles or sound waves. And they carry a net. These excitations, all these excitations then carry a net gravitational mass. Of course, for small particles like quantum particles, that's totally irrelevant from the viewpoint of gravitational field that it generates. But maybe for much more energetic sound waves like seismic waves, this can be measured. And so that's a question. And I don't know whether technologically it can be measured. Thank you very much.
So thanks for the very clear talk. Do we have any questions for Alberto?
Sorry. Hi. Can you reiterate your wavelength consideration? Does this imply this mass displaced relationship is only applicable to certain frequencies of sound waves and
not really. So do you guys see here? It's pretty dark. Can you still see here? No, you cannot see anything. If I write here, you cannot see.
Chalk might be a little more useful for some.
Where is it? This one, can you see? Yeah, okay. So the claim is this: I have a wave packet of some typical wavelength, lambda, no? And then this is an integrated relationship, okay? So in the way I derived it, I'm considering the whole wave packet as a single particle, let's say, and so I associate with it a gravitational mass. I can also, if I can resolve the wavelength, I can also make more local statements like what's the coarse-grained mass density associated with this wave packet is. But it can apply to any wavelengths, and as long, so at least in this way of doing things, as long as the wavelength I'm talking about, so the wavelength of my sound waves, are much smaller than the wavelengths of any other, I don't know, fluid modulation I might have, like, I don't know, some non-trivial flow, or some much longer sound wave, or the stratification coming from gravity. That's the only condition under which this effective point particle theory makes sense. Otherwise, you should use something else. But this is the only condition. Okay. For instance, let me give you an example. Suppose that you have such a rarefied, such a stratified medium that this is your object, but the density changes by a factor of 2 between here and there. Then I cannot use a point particle description of this. Okay, so I have to use a continuous description. So that's the only constraint.
Hi. So you mentioned, sorry, my voice. You mentioned earlier that you can derive this from the continuity equation and Euler's equations.
Yeah.
In that case, might it be easier to first try to measure the mass in numerical simulation rather than in experiment? I realize numeric fluid simulations are very difficult, but
I'm working on that with some students. Yeah.
Okay.
So far it hasn't been easier, but yeah, I think you're right. Meaning it sounds certainly easier than in an actual experiment, but we haven't figured out yet how to set up the simulation. Yeah.
thank you.
Thanks. So in the last slide, you showed these sort of interesting trajectories that I think wave packets would take if there's a dispersion relation like the one from superfluid helium.
Yeah.
Should I understand those cusps as occurring when the acceleration has taken your P down to the minimum, and so your velocity just literally flips direction?
Yes. So dp, so the net mass is positive, so dp over dt is always pointing downwards.
Okay.
So momentum wants to go down like this. But in doing that, depending on whether you start left of the minimum or right of the minimum, you can cross the minimum once, like in these cases, or twice.
And just twice?
Excuse me?
What
Just
happens?
twice.
Okay.
Twice, because twice corresponds to this. So I start from here.
Mm-hmm.
Wait, let me think about it. I start from here. So I had a. So let's say that this is this length would be P star. So the typical the momentum at the minimum. Okay. So I think the claim is this: if I start, let me think about it. I start here.
Don't you think you need also maximum with this curve? So
Excuse me?
do you need the maximum? This epsilon of peak has minimum and maximum. Are you using maximum as well?
I'm not using the maximum. I'm just working in an approximation close to the minimum. Yeah, that's the usual Roton approximation, because otherwise other phenomena become important. In particular, the maximum is unstable. So I have to think about it. So Px Px is conserved, and Pz is going down at a given rate. So let's say that if I put P star here, let me think about it.
Isn't it just that once it goes twice, it's
Yeah,
going
so
down?
exactly. If I start like this, so this is much longer than P star, so I'm right of the minimum. Okay. And then when I go down, at some point, I'm gonna cross this circle here, and I keep going down and here. So these are the two inversion points. Sorry. These are the two inversion points. So I'm right of the minimum, I go left of the minimum, and then right of the minimum again. It
Okay,
happens at
thank
most
you.
twice.
Thank you.
Could you explain why you use the hydrostatic equilibrium condition, even though
For simplicity.
just okay.
Because then you can come up with as many, if you want, experimental setups you imagine. But if you just want to consider what the analog of the Archimedes principle is for more general objects, Archimedes principle is usually a statement about hydrostatics. So we said, let's consider that. But you can use these Lagrangians or Hamiltonians to compute, for instance, scattering processes. If you have your object and you try to scatter a sound wave of it, what do you get? Stuff like that.
Okay, thank you.
Yeah, for simplicity, to talk about Archimedes principle is better, is easier to do it in hydrostatics. Yeah.
Is there maybe one last question for Alberto?
So you're working at some nonlinear order, sort of perturbatively. Is there any relationship between this mass you get and, I mean, when you have a shock wave, which is, okay, maybe stronger nonlinearity, but there's a net displacement of the air when it passes you. Is there any connection between those two?
That's a
pieces
very
of
interesting
physics?
question. I don't know. It's a beautiful question. So I want to emphasize, maybe related to this, is that we checked this formula at quadratic order, but in this way of doing things, when I derived it this way, there is no approximation beyond the small size approximation. Okay, so this is a fully nonlinear statement. So the claim is that if we keep going in this perturbative expansion of the equation, it should match to all orders. We stopped the quadratic order, so I don't know, but at all orders it should match. And so, yeah, it's a good question. Maybe I will have to think about it. I don't know. I don't have an answer.
Thanks.
So let's thank Alberto again for the great talk.